Okay, so let's start the lecture number 11, I think it is. And today's plan is to go through these reconstruction protocols. Let's recall what was our square phantom, and then go through the motions of simulating data with less inverse crime, maybe even no inverse crime, at least very little, and then try out Tikhonov and total variation. So first of all, let's recall what is our square phantom. So let's just open this one and recall this. We built previously in the course, and we did it in the way that we can look at the phantom with different discretizations. So the phantom has size m times m. So if we take 32 and run this, we see a phantom like this. So it's in a square domain, and we have 3 rectangles, which I think the geometry of the rectangles, I think we chose in a way that they don't agree with the boundaries of our square root of 2. So yeah, we have some kind of irrational numbers or something. So they are not really going exactly along the sides of pixels. And we can construct these at different resolutions. So we have kind of the same thing, same geometry, but with arbitrary pixelization. And we don't have to stick with powers of 2. We can, if we want, we can take some other numbers as well, and it should work. But however, I think mainly we will be working with square. What happened? Let's just mainly work with square root of 2 sizes. Okay, so next step, we did this radon matrix computation thingy, and how that worked. Let's recall. The idea was to first choose the size of our unknown. So this is j is just the power of 2 we are dealing with. That's the pixelization size, and then we choose how many angles we take spanning the full 360 circle. Because for each choice of j and none, we need to compute the matrix separately in this approach. And we did the computation in this rather inefficient brute force fashion by just computing it column by column by applying MATLAB's radon. But that's a kind of a simple and clear way to do it. Maybe not the fastest, but anyway, we can borrow the coding that has been done behind the radon routine. And then actually we also compute the singular value decomposition. And finally, we save the whole thing in a file in our data folder. The file is called radon matrix something. And what is that something? We include the power of 2, and we include the number of angles. So we have several files done, so we can later easily take them, just read them from file. This is more convenient than always compute it again, because this computation really is not so fast. It's not designed to be fast. And we save the matrix, the size parameters, the angles, and the singular system. All of this is saved. And let's see what we have in our data. What I did beforehand, I computed with 32 by 32 pixelization and with 2 choices of numbers of angles. And the same thing for 64 by 64 with the same angles, and 128 by 128 with the same angles. So we have 6 cases we can compare. Okay. So any questions about this stuff so far. Yep.
Yeah, but we avoid the crime here. It was like that.
Yeah, we have not yet simulated any data. We just built the matrix for the computational model.
Yeah. Okay.
So we are not yet in the question about inverse crime is what do we do next?
Yeah.
Do we just simulate the data by multiplying with that matrix we built, or do we do something else? And we'll do something else, although in this number 2 thingy, just to try out our method, what we did here, we are committing inverse crime. We are committing inverse crime. This was our just first check we did. So we picked some resolution, some angles, we loaded the matrix, we built the phantom. Then here, this is the inverse crime. We build our data by just multiplying by the matrix. And then we actually used truncated singular value decomposition to reconstruct. So let's see. So we see this is what happened. We see the non-zero elements of the matrix here. And just to remind you what we see, these blue things, they are not lines. They are actually, if we zoom in and we zoom in more, they are just points showing which entries are non-zero in the matrix. But they are just so close to each other in this full view that they look like lines, but they are not lines. And then singular values, the red ones are the ones we use in the truncated SVD, and you see the ill-posedness in how these singular values become small. Again, note the logarithmic scale. Here is our reconstruction using those singular values and singular vectors up to that point. This is how it looks like. And now, of course, we can change our alpha if we want. We can, for example, use some more singular values. So now we are going a little bit further with these red points here. And we get, well, a little bit different reconstruction anyway.
Noise here.
We didn't have any noise here. No noise. And I think we could even, let's put here also naive inversion. Naive inversion would be this would be now our matrix A is not square, so we can't do this. It doesn't make sense. However, as you may recall, we can do so we could do this. We learned previously we take the inverse of ata and we multiply. Oh, sorry, this is sorry, later. Sorry. So this would be the least squares solution we derived. So let's try that one, and let's just do it here and plot it. Let's close the previous windows and put image scale. I think we need to reshape, and we have this naive reconstruction m by m size. No picture. Why? What happens? Oh, here. And actually, let's not distort. Let's have the axis. No, sorry. So now the square phantom looks square. Okay, we get a perfect reconstruction using, yep.
So that basically is the same, we just took the alpha, the whole so
Yes.
Without, using all.
Yes, that would be the same thing. Yes, exactly. Good point. So actually what we did was to use all singular values, but without going through the, well, we could see.
We take alpha as well size.
Yes. Length swalls. Yes, that's what it is. So we get a perfect inverse crime reconstruction, and to reveal the crime, what we can do, let's actually, that was actually a really good suggestion. Let's so naive inversion, yeah, that's better. That's a nice way to do it. But now if we put here noise, let's see what happens now. We get something completely wrong immediately. Even I think if we put small noise, even extremely small noise immediately comes here. This reveals that we are dealing with an inverse crime. So that's one way to detect it, the inverse crime, add noise. But even better way is to really simulate data with a different method than multiplying by the actual matrix. So let's leave naive inversion as an option there. So that was just the naive approach, and then.
Can you show
Yep.
the CSVD with the noise?
Yeah. Oh, yeah, of course. Yes. Yeah, just. So there, the noise doesn't really bother. It's a robust method. So that's really good. Good point. So this is what the course is all about: finding reconstruction methods that are robust against noise. If there's little noise, we should be computing images that are not affected with a little noise. So they may look a little bit wrong, like this one is too smooth and not so perfect. But however, the most important thing, it is robust against noise. That's somehow the holy grail of inverse problems. And now, of course, once we have, for example, this method, truncated SVD, which is robust against noise, now we have something. But the next step, of course, is to move forward and try something maybe better or different options of enforcing a priori information. All right. Maybe we can also try just a couple of examples with just very few. So here we are using just the 21st, and I think this should be extremely robust to noise because we are using so few. So if you put here 1,000 times more noise, the picture is the same. You see, this is robustness against noise. I put 1,000 times bigger noise, but pretty much no effect. I think we can even put more. So this is 10,000 times more. This is 100,000 times more noise than we had before. Still, you see, no effect. This is robustness against noise. We are now dealing with heavily noisy data, but severely truncated SVD doesn't mind. But it always gives a reconstruction that is a linear combination of the singular vectors, and that's not always what we want. I think let's keep this option of having noisy data. And here let's keep this as it was. Okay. So that was the truncated SVD and inverse crime data. So next let's do the avoidance of inverse crime. So I wrote up this file based on the previous course of 2015. I just updated it to match this year's notation and phantom. So let's see what happens here. Let's take the same case we were just looking at. Let me just first run this and see what's happening. So on the left here is the sinogram with inverse crime. So this is just multiplying our phantom with 3 rectangles, dropped as a vertical vector, multiplied by A, and then reshaped back to 32 by 32. Oh, sorry, this is the sinogram. So, well, horizontally it's the number of angles, and vertically it's the number of pixels in the virtual detector that MATLAB chooses for us. In the middle we have a sinogram computed by avoiding the inverse crime with two different tricks, and on the right you see the difference between the two. I subtracted them so we can see where there is difference and how much. And we can do the same thing with higher resolution. So this is 64 by 64 case. So now you see the sinograms are a bit closer to each other. This is the error is more like purely 0, not really, but closer to 0. And we still had this option of doing 7. Takes a bit longer to compute. Maybe because we are loading in the singular system, although we wouldn't really need to do that. And here it's maybe even closer. So what happens here is actually the same thing. I think I'll remove, I don't think we need these big matrices, and we don't need them here. So let's see what happens. So we load from the disk our matrix we had before, but not really. The matrix is not the main thing. I think maybe the main thing here is the set of angles we have been using. I don't know.
Are you now, you have J defined in this file, and you are also loading J from the file, like from the previous results.
Yeah.
Should that be when your?
Yeah, it's here. Yeah. So
are those meant to be the same, or
they will be the same, because this here specifies which file we are loading, and to the file specified by a certain number J, it will contain the same number. Or it's
you don't need to define that up then.
No, and we have also, well, M we can load, and I'm not sure if we need, I don't think we need N, and I don't think we need these. Oh, well, errors we can have. Yeah, I think we really, and I don't think we need even the matrix A.
It was inverted in follow.
Where?
Yeah. Yeah. Yeah, you have, yeah, the N angles is defined above, so you don't need to load it.
Which one is defined?
N and
Yes.
below J.
Yeah. So now I think this is all we need, maybe. Okay. So let's see. Oh, and anyway, here I put already here in the beginning to choose how much noise we take. So relative noise level would be like 1% now. And yes, okay, so here we choose the resolution of the phantom. Let's do it first with 32 by 32. The number of angles. And actually, we specify that we use the specific set of angles defined before in the radon matrix computation. So here we take in, and actually the main thing to take in is just the angles. The capital M we could compute because it's just 2 to the power of j. So there's nothing magic about that. But the set of angles is important, and that was defined previously. So what happens next for constructing the data, this is for our square phantom. I left there from the previous file if at some point we want to do something with the so-called Shep-Logan phantom. So that's there, but it's now commented anyway, so we don't do it now. But now we use our square phantom, and then here let's just compute using radon. Let's compute the sinogram of our phantom F using exactly those angles. So this is actually the same thing that our matrix A is doing by multiplying, because the matrix A was built using this radon operation. So that's, yeah.
If our square phantom contained more circular shapes inside, would it be easier to reconstruct? Because the reconstructions, when we look at them, they look quite fuzzy around, so they look kind of more circular rather than rectangular.
Right. We can try with different phantoms. Let's first do this with the rectangle phantom, and then we can actually shift to this Shep-Logan phantom, which is very different. So we'll see what happens.
Is phantom a command defined in MATLAB? Or
This Shep-Logan, this command phantom, it's really meant for this Shep-Logan. The Shep-Logan phantom is something quite standard in X-ray tomography studies. So this is the inverse crime data, but then we want to compute it in a different way, avoiding inverse crime. And the trick here, the trick we use is to compute with higher resolution, to double the resolution. So we take M2, which is twice M. So actually now we move, M2 will be 64, in our case now. And then we build our phantom at size 64 by 64. And remember, we constructed our phantom in the way that it kind of builds the same phantom in the unit square. And the more we pixelize, it's kind of the same geometric shape, just with more and more accuracy. Then what we do, we use the radon command for the higher resolution thing, using, well, here are the same angles, but to add more errors to the data to really avoid inverse crime, I'm actually also putting random error to the angles themselves, meaning that maybe our tomographic machine is vibrating a little bit, or we are not really measuring along the same lines, to make some modeling error into the data. So then let's record what is the ratio between our two data sets. And then actually as you may remember, in the radon transform, this second, what it returns secondly here is the variable along the projection, along the detector. So it's a one-dimensional coordinate along the detector. So what happens here for MATLAB, this phantom is twice bigger. So like for example, and for MATLAB, the pixel size gives the geometric size of the phantom. So our first phantom would be defined from, I think, from 0 to 32, both x and y direction. Although we must think that it's in the unit square. That's what we think, and that's what we want to model. But MATLAB in the radon file, it takes in the pixel image and it thinks it's defined in the square from, in this case, from 0 to 64, both x and y direction. And that's why also the coordinate along the detector is much longer, twice longer now in this case. So that's why we need to compensate for the coordinates that come out of here. We need to multiply them by this ratio, so then we get comparable coordinates to our lower resolution case. And then there is this rather technical area where we have to deal with the different location of the origin. Maybe I think after the break I could maybe comment about this stuff a little bit, if it's confusing. I kind of guessed this might be a confusing place. We could discuss that a little bit on the blackboard after the break. And then that may actually be pretty much the main point how this whole thing is done. So I think let's have the break now, and after the break briefly look at the blackboard, what is going on.